Hello everybody, here is the final exam review class video, part 2. We're going to work on 29 through 43 odd from our review packet. Number 29, solve the inequality and state the solution set in interval notation. X plus 6 divided by x plus 1 is less than 2. First, we need to subtract 2 from both sides. We will get x plus 6 divided by x plus 1 minus 2 is less than 0. Remember to leave some space for yourself. In order to subtract these two fractions, we need a common denominator, so multiply the numerator and the denominator by x plus 1. Remember that subtraction is the same thing as adding by the opposite, so now we won't forget to distribute the negative 2 to both terms. So distribute and combine the fraction to get x plus 6 minus 2x minus 2 in the numerator and x plus 1 in the denominator. That fraction is less than 0. Combine like terms and get negative x plus 4 divided by x plus 1 is less than 0. So now the problem should be a little bit more clear. We're trying to find all of the x values where this fraction is less than 0. In order to do that, we're going to find the key points. That is, we're going to find the x-intercept and the vertical asymptotes. The x-intercept occurs when the numerator equals 0. So set negative x plus 4 equal to 0. We will end up getting x equals 4. So the x-intercept is the point 4, 0. To find the vertical asymptote, set the denominator equal to 0. We get the vertical asymptote x equals negative 1. Now it's time to build our test intervals. Something important happens at negative 1, something important happens at 4. At negative 1 we get a vertical asymptote, and at 4 we get a 0. Remember that in our solution set we are not including the zeros. In each interval we'll pick a test value to evaluate our function. In the interval negative infinity to negative 1, we can choose x equals negative 2. We're going to plug a negative 2 into this function right here. So when we plug in negative 2, we get a positive number in the numerator divided by a negative number in the denominator. Positive divided by negative is negative. So the function takes on negative values when x is less than negative 1. Now we need a test value between negative 1 and 4. We can choose x equals 0. Plugging in a 0 we'll get a positive number divided by a positive number. So the function is positive in this interval between negative 1 and 4. Now we need a test value that's greater than 4. We can choose x equals 5. When we plug in 5 we'll get a negative number in the numerator and a positive number in the denominator. Negative divided by positive is negative. So the function takes on negative values when x is greater than 4. We are looking for the x values that make this function negative, so we can shade the negative areas. Alright, vertical asymptotes are never included, so we're shading everything less than negative 1. It says do not include the zeros, so we're not including 4, and we're shading everything greater than 4. So our solution set is the set of all x such that x is in the interval negative infinity to negative 1, union 4 to infinity. Number 31. Complete the square to manipulate the quadratic equation into standard form. Okay, step 1. Circle the first two terms. Step 2. We need to factor out a 2. We'll get 2 times x squared plus 10x minus 5. This is the square that we need to complete. In order to complete a square, we need to add something. We should take a look at the 10. We should do 10 divided by 2 and then square it to get 25. So to complete the square, we have to add 25. By writing plus 25, we're actually adding 50 now because we can't forget about this 2 in front. So to compensate for adding 50, we also have to subtract 50. Make sure we check our work. We should check to make sure that this line and this line are equivalent. So now we can factor and simplify to get 2 times x plus 5 times x plus 5 minus 55. That means that h of x equals 2 times x plus 5 squared minus 55. We have just completed the square of the quadratic equation into its standard form. Number 33. Given f of x equals 2x squared minus 5x, evaluate the difference quotient. In evaluating the difference quotient, we need to know what f of x plus h is. So first of all, we're going to find f of x plus h, which means into f we need to plug in x plus h. So instead of these x's, substitute in x plus h. Ding, 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 ding. We get this, which we have to simplify. First, we can rewrite that x plus h twice, since we squared it. Next, we can distribute the x plus h's, and we can distribute the negative 5. Make sure we distribute the negative 5 to both terms. And finally, we can distribute the 2. We should notice that there are no like terms here. So therefore, check, we have f of x plus h. Check, we have f of x because that's given in the problem. So we're ready to evaluate the difference quotient. The difference quotient equals, first, substitute in f of x plus h. Next, we have a minus sign, and we should substitute in f of x, which is 2x squared minus 5x. It's important to use parentheses here because we need to distribute this negative to both terms. And we have divided by h. Next, rewrite and distribute the negative to both terms. We should see some cancellations. So 2x and negative 2x cancel, negative 5x and 5x cancel. We're left with 4xh plus 2h squared minus 5h divided by h. In the numerator, notice that we can take out an h. So we have GCF factoring in the numerator. And lastly, we can see that the h's cancel. So the difference quotient is 4x plus 2h minus 5. Number 35. Factor completely. X cubed minus 4x squared plus 25x minus 100. We can notice that this is a factor by grouping problem. So, circle the two groups. From the first group, we can factor out an x squared, and we're left with x minus 4. From the second group, we can factor out a positive 25, and we're left with an x minus 4. We should continue to observe the two groups. We can see that there's a GCF. From both groups, we can factor out an x minus 4. So, take out an x minus 4. We're left with x squared in the first group, and we're left with positive 25 in the second group. This can be factored further. We're noticing that we have the sum of perfect squares, which can be factored. We got x minus 4 times x plus 5i times x minus 5i. So now we've factored completely because we have a product of 3 linear factors. Here's a reminder about the sum of perfect squares. We can always check our answer by distributing. We can use our first last technique. X times x is x squared. 5i times negative 5i is negative 25i squared. And we should remember that I squared is equal to negative 1. So that's equal to x squared plus 25. So if we see x squared plus 9, we should recognize that as the sum of perfect squares. Its factors are x plus 3i, x minus 3i. We should not confuse this factoring technique with the difference of perfect squares. So x squared minus 9 is a difference of perfect squares that factors into x plus 3, x minus 3. Number 37, solve for x. 0 is less than or equal to x, and x is less than 2 pi. We're trying to solve the equation cosine squared of x plus 2 sine of x equals 2. First, subtract 2 from both sides so that we have trig equation equals 0. Next, notice that we want to factor, however we can't factor yet because we have cosine terms and sine terms in the same equation. So we have to make a change. Cosine squared of x is 1 minus sine squared of x. Now we have a trig equation that has all sine terms, so we can combine like terms. That means we're combining the 1 and the negative 2. We can multiply both sides of this equation by negative 1, which effectively changes the signs. And now we have something that's factorable. Sine x times sine x is sine squared of x. The factors of 1 are 1 and 1. The signs both need to be negative, so that we'll get a negative 2 sine of x. Tea time! On both sides we get sine of x equals 1. So we're looking for the angle whose sine is 1. That angle is pi over 2. So our solution is x equals pi over 2. Number 39. Solve for x. E to the 2x plus 3e to the x equals 28. We should recognize this as a factoring problem. Before we do anything, we have to subtract 28 from both sides. That way we get exponential equation on one side and 0 on the other side. Next, we should recognize that e to the 2x is the same thing as the quantity e to the x squared. Once we recognize this, we can factor. E to the x times e to the x is e to the x squared. The factors of negative 28 are positive 7 and negative 4. Those are the factors that will get us a positive 3 e to the x. Tea time! On this side we get e to the x plus 7 equals 0. On the other side we get e to the x minus 4 equals 0. So on the left we get e to the x equals negative 7, which we can reject because there are no x values where that exponential function will take on negative values. On the right hand side we get e to the x equals 4. To solve for x, ln both sides. So we also have to ln this side. We get the ln of e to the x equals the ln of 4. Whee! Slide rule. X times the ln of e equals the ln of 4. Remember that the ln of e is equal to 1. So x times 1 is just x. X equals ln of 4. Here is our exact answer. Now over on the left hand side, when you got to e to the x equals negative 7, you may not have realized that you can reject. If you didn't realize, then you could ln both sides, do your slide rule, and you'd get x equals the ln of negative 7. If you plug in the ln of negative 7 in your calculator, it'll give you an error. So that's when we could have known that we would have to reject that side. Finally, as a quick reminder, why are we getting this error? Well, here's a graph of the function f of x equals the ln of x. You can see that if you plug in a negative 7, say over here, then you don't get a value. So that's why your calculator is spitting out an error. Hey, just for fun, and since we're all in a good mood, here's number 40. Solve for x. 5 ln of 4x plus 13 equals 23. Step 1, subtract 13. Next, divide by 5. Next, remember that ln really means log base e. So we have log base e of 4x equals 2. That's equivalent to e squared equals 4x. So to solve for x, divide by 4. X equals e squared divided by 4. That is our exact answer. Number 41. Sketch the graph of g of x equals negative 2x cubed plus 8x squared minus 8x. First, we should use the leading coefficient test. In this problem, n, which is our degree, is 3, and the leading coefficient is negative. So our degree is odd, leading coefficient is negative. That means we're dealing with a reverse Johnny Travolta. Our conclusion about the end behavior is that On the right hand side we have a fall, and on the left hand side we have a rise. Right fall, left rise. Next, we should find the zeros. To do that, factor out a negative 2x. We see that we can continue factoring x squared minus 4x plus 4. We'll get x minus 2 times x minus 2. So that means that negative 2x times x minus 2 squared equals 0. Therefore, our roots are x equals 0 and x equals 2. X equals 0 occurs with a multiplicity of 1. That's because this exponent up here is 1. That means that the graph will cross the x-axis when x equals 0. X equals 2 occurs with a multiplicity of 2 because of this exponent. So that means that the graph will bounce off the x-axis when x equals 2. Now we should build our test intervals. We have an x-intercept at 2 and 0. We know that to the right we get a fall, and to the left we get a rise. We know that our graph has to cross when x equals 0. It's going to have to come back up, but when it gets to 2 it's going to bounce, and in this case it's going to bounce down. So here's the basic shape of our graph. Now we just need some points on our graph. So when x equals negative 1, we get the point negative 1, 18. If we wanted to get that point by hand, we would plug the negative 1 right here into the factored version. By plugging in a negative 1, we get negative 2 times negative 1 times negative 3 squared, which gives us positive 18. Or we can just use the table function in our calculator to get the point negative 118. Next, plug in x equals 1 to get the point 1, negative 2. Finally, plug in x equals 3 to get the point 3, negative 6. Using all this information, we can sketch the graph. So we get the point negative 118, 0, 0, 1, negative 2, 2, 0, and 3, negative 6. Remember that polynomials have nice smooth curves. There are no sharp points like in absolute value functions. If the directions say to label the points, then you can label them like this. Hey, guess who's getting crazy right now? That's right, we're about to do number 42. Sketch the graph. h of x equals log base 3 of x minus 1 plus 5. To graph this, we can analyze the parent function. In fact, step 1, state the parent function. F of x equals log base 3 of x. It's important to make sure that we're naming our parent function with an f and that we're putting an x right here. Parent functions have parent points. When we plug in a 1, we get log base 3 of 1, which equals 0. Go ahead and check it. 3 to the 0 is 1. When we plug in a 3, we get log base 3 of 3, which equals 1. You can check this as well. 3 to the first equals 3. We learned that the log parent function has a vertical asymptote, x equals 0. Next, write h in terms of f. h of x equals f of x minus 1 plus 5. That's why it's important for us to name our parent function with an f. That way this f right here will actually mean something. Next, state the shift rules. In order to graph h of x, we need to take our parent function and move right 1 up 5. So we need to sketch our parent function. Here are the points 1, 0 and 3, 1. We also have the vertical asymptote x equals 0. Now we shouldn't get too crazy when we're drawing this parent function. So when we plug in a 9 for x, we get log base 3 of 9. That's equal to 2. So go ahead and check yourself. 3 squared equals 9. So the point 9, 2 is on this graph. Okay, log functions hug the vertical asymptote, and when it gets to these points it's going to shoot out like this. And it's not going to increase very fast. Okay, so there is f, our parent function. Now to graph h of x, we're going to go right 1, up 5. So the point 1, 0 becomes the point 2, 5. 3, 1 becomes the point 4, 6. 9, 2 becomes the point 10, 7. The vertical asymptote also gets moved right 1. So the new vertical asymptote is x equals 1. H of x will have the same basic shape as f of x. So again, it's going to hug the vertical asymptote, but when it gets to these 2 points, it's going to shoot out. So there's h. As a follow-up question, you might be asked for the domain of h. You can look at the graph for that, and you'll see that you can also answer that question algebraically by looking right here. For log functions, we know that x minus 1 has to be greater than 0, so that means x must be greater than 1. Well, I guess we veered off a little bit from our original plan. Here's number 44. We're going to sketch the graph of y equals 4 cosine of 2x minus pi over 4. First, write this down so that you'll be organized. Next, a equals 4. That means that the amplitude is 4, so now we can build our range. Negative 4 is less than or equal to y, and y is less than or equal to 4. b equals 2. The period of a cosine curve is 2 pi divided by b. So 2 pi divided by 2 is equal to pi. That means that the length of our interval is pi units. Next, we have to come up with cycle start and cycle end equations. For a cosine curve, the cycle starts when 2x minus pi over 4 equals 0. The cycle ends when 2x minus pi over 4 equals 2 pi. So now we'll solve each equation, add pi over 4 to both sides, and then divide by 2 or multiply by 1/2. We get that our cycle starts when x equals pi over 8. To find where our cycle ends, also add pi over 4 to both sides of the equation. 2 pi plus pi over 4 ends up being 9 pi over 4. That means that 2x equals 9 pi over 4, divide by 2, or multiply by 1/2, and we see that the cycle ends when x equals 9 pi over 8. So here is our interval where one cycle occurs. The length of that interval is pi units. Remember that we found the length of the interval up here when we found the period. Now to graph our cosine curve, we have to divide that interval into 4 equal sections. I'm circling denominators because it would be easiest if we had a common denominator. The common denominator is 8. So that means we're going to be counting by 2 pi over 8 on our x-axis. So now we need to take all of this information and make a graph out of it. Remember that our cycle starts at pi over 8. We divided our interval into 4 parts, so put 4 slash marks. The directions are going to say to draw 2 cycles of our curve, so I drew 4 slash marks forward and 4 slash marks back. Since we're counting by 2 pi over 8s, we'll get 3 pi over 8, 5 pi over 8, 7 pi over 8, and 9 pi over 8. Going backwards, we'll get negative pi over 8, negative 3 pi over 8, negative 5 pi over 8, and negative 7 pi over 8. Next, draw the y-axis. The y-axis happens when x equals 0, that's between negative pi over 8 and pi over 8. Since our amplitude is 4, draw 4 slash marks going up and down. Beginning at pi over 8, cosine starts at its maximum value, which is 4. It goes down to 0, down to its minimum value, up to 0, and ends its cycle at the max. It'll do the same thing on the other side. Then we can draw our cosine curve. The directions might say to plot and label the key points. The key points are the points that occur in the interval that we found right here. So the key points are pi over 8, 4, 3 pi over 8, 0, 5 pi over 8 negative 4, 7 pi over 8 0, and a 9 pi over 8 4. We should end this video with a reminder of how to fill out a blank unit circle quickly. First, we can fill out our degrees. We're going to count by 45s. 0, 45, 90, 135, 180, 225, 270, 315, 360. Next, we'll count by 30s. 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. Now we'll fill in the radians starting with 0. Again, we'll start with the 45 family. That means we're going to count by pi over 4s. 0, 1 pi over 4, 2 pi over 4. Notice how I reduced. 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Now we'll count by pi over 6s. 0, 1 pi over 6, 2 pi over 6. Notice how I reduced. 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. Now we can fill in the points. I'll start with the story of the x values. X starts at 1. We have root 3 over 2, root 2 over 2, 1/2, 0, negative 1/2, negative root 2 over 2, negative root 3 over 2, negative 1, negative root 3 over 2, negative root 2 over 2, negative 1/2, 0, 1/2, root 2 over 2, root 3 over 2, 1. Finally, we'll fill in the y values, starting with this y value right here, which is 0. 1/2, root 2 over 2, root 3 over 2, 1, root 3 over 2, root 2 over 2, 1/2, 0, negative 1/2, negative root 2 over 2, negative root 3 over 2, negative 1, negative root 3 over 2, negative root 2 over 2, negative 1/2, and 0. Remember that each point xy gives the cosine and the sine value for each corresponding angle. We also labeled the tangent values on our unit circle. To find the tangent values, you can always do sine divided by cosine. Those values are as follows. Root 3 over 3, 1, root 3, undefined, negative root 3, negative 1, negative root 3 over 3, 0, root 3 over 3, 1, root 3, undefined, negative root 3, negative 1, negative root 3 over 3, 0. Here are all the trig formulas that will be given to us on our reference sheet. We have to know the Pythagorean identities. So, here are the Pythagorean identities. So we should go back into our notebooks and look at those Pythagorean identities, and we should memorize them. If you want, there was a section in our notes where we derived all of them algebraically. But somehow we have to get these Pythagorean identities into our brains. Okay, so that concludes our final exam video. Good luck on your final, and have fun.